when I tested this out, it was just myself, so it was really strange. Right, meeting is now live streaming live on YouTube. Let me just get you the link. It's loading.
This is a YouTube link, right?
Yes, yes.
Did you send it by email or in the chat?
Not yet. It's just loading.
Oh.
Right, I think that's it now.
This is quite easy. Some people can.
Hi guys.
Hi.
So it looks like I'm the only one with an old computer who can't create a background, so everybody sees the mess behind me.
Just paint your room red or blue or something, or put a big poster behind you.
That's right. Or hold a towel.
Yes.
We had it was my colleague Ollie's birthday at the weekend, so we all had birthday templates.
Oh, how nice! How nice! Oh, I like it.
So we all logged on. Yeah, I'll put it back to my bland.
Your bland one, yeah, that's right.
Yeah. There you go.
So at the end of okay, oh, YouTube, perfect.
I can see. I can see me on YouTube now.
We had it was my colleague Ollie's birthday. Oh, I can hear myself. We all had birthday.
What's happening? Oh, how nice! How nice! Oh, I like it.
We all logged on. Frank, if you mute the YouTube video, that'll.
Oh, sorry. Yes,
right.
sorry.
There you go.
So, at the end of okay, oh, YouTube, perfect.
I can't find it now. I have too many windows open. Just a moment. See me on YouTube.
Okay, well, I guess we'll mute Frank for the time being.
Oh, I can hear myself. We all had birthday.
What's happening?
There you go. I've muted Frank for the time being.
Okay, thank you. It's bad enough to talk online. You don't actually want to hear yourself on top of it. Were you in touch with Lara?
Yeah. I've sent her the link a couple of times. She responded yesterday. So to say that she would like to dial in early to run through her slides. She's not in the waiting room at the moment.
Okay.
So, oh no, right, speak of the devil, there she is. Frank, are you? You're muted. Sorry, Frank.
I have to unmute myself. Okay, sorry. I couldn't find the YouTube video, so it was running in the background, and I had 20 windows open, so I had to find it. So now I found it and shut it down. It
Perfect.
works.
I had to mute it as well, so I couldn't hear myself. Okay. But it's working, so that's good. Hi, Lara.
Hi, Lara. Nice to meet you.
I think you're muted.
Or maybe you should unmute.
I think Lara is muted.
Yeah, I cannot unmute. Lara, can you mute?
The bottom left-hand side. Oh, there we go. Got it.
Okay, excellent.
Okay. Can you hear me now?
Yes.
Okay.
Hi, I'm Frank. So I will make the introduction today.
Hi, Frank. Nice to meet you. Thank you.
And I think, yeah.
We were in contact once about the conference in Mexico in Oaxaca, I remember.
Yeah.
Which actually is cancelled now, so we don't know what's going to happen.
Oh, no, yeah.
But yeah, and thanks for the suggestions for replacement speaker. We will see. Maybe you're interested next year if it happens. We will send you another email.
Yeah. That's true. Actually, I thought about it another time. I was like, oh, why did I not want to come? It sounds more interesting now. I think I heard some talks that were related to birational geometry and rationality problems. I was like, oh, this is quite interesting. I think this might be also a topic in your workshop.
Yeah, I think we did a lot of work to invite speakers and try to find speakers, and now we had to do a lot of work to cancel everything, which is really terrible. So we hope they will postpone it, but we don't know yet because it's obviously a financial issue and we have to see. But
yeah,
I'll let you know.
Yeah, thank you.
It's great you could come to our seminar now. That's great.
Yes. And thank you for adjusting the time.
Of course.
I thought about it. It would have been 7 a.m. for me, and I really thought about, okay, well, if I get up at 6, but then I thought, no, probably at 7. Usually I sleep until 7 or 8, so I would probably not perform very well giving a talk.
One question: do you have any slides you are using, or you just right away?
Oh, yeah, I have slides.
Do you mind sending them to us? Then I can send them through the chat so people have them already.
Sure. Maybe I can also put them here.
Either you send them. I think you probably can send them through the chat, right?
Yeah, you can add a file.
Just send it to everyone, and we have it there. We can just tell you at the beginning that. Because sometimes easier people have problems with connections, and then they can see the slides by themselves while listening.
For sure, yeah. So I sent them in the chat. Maybe you can check if it works.
Oh, yeah.
I think we have to resend them later because I think people who join later don't see the chat earlier, but that's not a problem.
Okay.
Perfect. Lara, would you like to just test that your screen sharing works? Well, it will work. Let's just.
Let's see. So here, that's the one I will use.
Perfect. I can see that.
Okay, great.
Yeah, and now the slides are changing.
Oh, sure.
I think I always have to click on the screen before I can change, but it's fine.
Perfect. I'm just going to double check that. Well, make sure that my screen sharing is working. Okay.
Yeah.
Slideshow. Done this so many times today, though. From the beginning. Hide floating meeting control. There we go. Frank, is that okay? Can you see that okay?
Moment. I have some problem with that. Okay. Yeah, that's fine. So I think I have the...
same as last. Oh, sorry.
Sorry, I was wondering, is it so are you turning the pages, Liam, or is Frank able to turn the pages?
It's myself.
Okay.
Frank, do you want me to email you the slide so you can do it? It's totally.
Do it because I just realized that my computer is running in the in the last. I think otherwise I would have to reconnect or something. So it's better if you just. I can see them. If you start, with the next seminar, I think we should start with that, and then.
Well, first maybe say hello in housekeeping, and then the next seminar, and then introduce Lara.
Housekeeping.
Yeah. Let's housekeeping next week, and then on to today.
We have 3 slides.
Well,
right?
so maybe today this is great, and then go back to Lara after that.
Yeah.
Perfect.
Perfect.
Cool. So what time are we at? I've got 5 to 4.
Well, thanks again for organizing this, Liam.
No, it's totally fine. You keep me busy, so I'm happy.
So there will be,
I've lost my controls.
By Polychok, which is also at the same time in 2 weeks, or in 3 weeks actually. I have to check, but so
sorry, Frank. What did you say?
Yes, there will be one more seminar which will be at 4 o'clock because it.
2 weeks time, isn't it? Yeah.
Yeah, but I think.
And Liam, we're inviting people for September. I think maybe you saw. I hope that's okay.
Yeah, that's perfectly okay.
And then we were thinking of taking a break in August.
Okay. A little summer break.
A little summer. Well, I don't know. We might regret it, you know. Then we'll just start earlier, end of August, if we get too bored. But I don't know.
Fortunately, I have to deal with students' admissions in August. We have clearing, which is another time.
Oh, well, it was announced today that Scotland is going into phase 2 of Back to Life, and the dentists are going to open on Monday.
Oh.
But wow. Unfortunately, outdoor hospitality, i.e. beer gardens, are not open for another 2 weeks or so. So I think that's all that people really care about, isn't it?
And also, frankly, I mean, it's probably safer to be in a beer garden than at the dentist. But hey, at least.
Yeah. Oh, and apparently the zoos will open. You know, I'd rather go to a beer garden.
Probably Scotland should close the borders to England just to be safer.
Yeah.
Well, it's funny actually because England are a little bit ahead of us. Their cinemas are opening and whatnot, and so yeah, Scotland seems to be doing it differently. So
I think Jordan did a better job in all of this so far.
Should we start letting people in? What do you think?
Yes, yes. So I'm distracting myself talking about beer gardens. Right, okay. I will let everyone in and then I'll turn the waiting room off so that we don't have to look at it.
Okay, cool.
Put the slides on, right?
Admit all.
Okay.
Participants.
How are you?
Hey, Hipólito, you have a really nice background.
Yeah,
Leicester.
yeah, of course.
Beautiful.
Yeah, this is back in my hometown.
Yeah, it looks amazing. And how do you do this? All of you, no, Sibylle, no, but all you other guys have these nice backgrounds, no?
You have the option in your video.
You can change. If you go to references where the wheel is, and then you see virtual background, and then you can take the ones which are there, or you can upload your own pictures, whatever it is, and then you can put them in the back.
Oh, wow.
So that's what I did.
I just looked for a spot in the house that has a white wall as a background. I don't have to worry about that.
Yeah.
Wait 2 more minutes, maybe.
Yeah, I will mute my.
Yeah, so I hope you can all hear me. Welcome to another edition of the LAGOON Leicester Algebra and Geometry Open Online Seminar. Today we have a different time. I hope everyone saw it. And sorry for those who can't be here with us, but it was just easier for speakers from Mexico. We have one more from California, which will also be at this time. So before we start, let me just mention a little bit of housekeeping as usual. So microphones will be muted, except the speaker and the chair, the hosts. Please rename yourself so that the first and last names are clearly visible. We know who you are. And please use the chat function to everyone to add name, question with your name, and give if you have questions. We're happy. I think Lara will be happy to answer them. If she doesn't see them through the chat, we will do it afterwards. We have a bit of time to do that. And yeah, if you want to do any meeting arrangement questions, then you should go to a private chat. So just to mention, next seminar will be at usual time at 1 o'clock again on Thursday, the 25th of June. We have Wendy Loban from Antwerp, and she will talk about linear quasi-categories as templicial modules. Okay, so now we can start. So it's a great pleasure to welcome Lara Bossinger from Instituto de Matemáticas in UNAM in Oaxaca, and she's going to talk about families of Gröbner degenerations. I should say that we have already put the slides in the chat. If you cannot download them, just let me know and I will resend them. So, Lara.
Great. Thank you for the introduction and the invitation. And well, adjusting the time, I hope at least enough people can come to this time and note the time difference of the seminar. So as you already mentioned, I'm going to talk about, the title of my talk is Families of Gröbner Degenerations. And this is joint work in progress with Fatime Mohammadi and Alfredo Najera Chavez. So let me start with an overview of my talk. I'm going to give you a short motivation for why I do what I do. I will review a bit of Gröbner theory because I was informed that the seminar has like a mixed audience in between algebraists and geometers or algebraic geometers, so I don't assume you know Gröbner theory by heart. Then I will come to the construction and main theorem of our project, and afterwards I will go into details of two applications. The first one may be more interesting to algebraic audience, is about universal coefficients for cluster algebras. And the second one is about toric families that might be more interesting for algebraic geometers. But I should say about the second application, it's right now more of an observation of a connection to toric families. So maybe application is a bit of is advertising very well our project. Okay, so let's start with the motivation. For most of this talk, I will be, I have in mind a projective variety that I'm interested in, or a bit more generally, it might be a weighted projective variety. And I want to understand how different toric degenerations of this variety are related. So that is interesting eventually to you already. If not, I will borrow this following slogan from mirror symmetry. They have the philosophy like for mirror symmetry of Fano varieties that knowing all possible toric degenerations of a variety is equivalent to knowing its mirror dual variety. So we follow a bit like this slogan and study a bunch of toric degenerations at the same time of the same variety. And in today's talk, I will focus on a more particular class of nice properties of toric degenerations. So I will have in mind a polarized projective variety and a bunch of toric degenerations of this variety that share a common basis. And I put this in quotes because that's not a technical term so far, but I will throughout the talk get back to this and tell you instances of what I mean by share a common basis. If at any point you have any questions, like as simple as they might sound, please just go ahead and ask. I'm happy to answer them or put them into chat, and I will try to get back at it. Okay, so let's start with the review on Gröbner theory. In my situation, I will be dealing, I think of varieties as the vanishing set of their ideals. So I will be dealing with ideals in a polynomial ring. With its elements are going to be polynomials, and if I have a polynomial, I can write it like as a sum of monomials. I can express it in the basis of monomials of the polynomial ring, and then this is my notation. So if f is a sum of some monomials x alpha, where alpha is an element of z to the n greater or equal to 0, then I denote by bold x alpha the monomial who has exponents alpha 1 to alpha n. And C alpha will just be a coefficient in the complex numbers. Now, if I take an element of R to the n, I will think of this as a weight vector that gives weights to my variables. And I can compute the initial form of f with respect to w. That is, I look at every monomial that appears with non-zero coefficient in f, and I take the dot product or the usual inner product of w with the exponent vector. And then I compute all these dot products, and I only keep those monomials of f that appear, that have minimal weight with respect to w. So this initial form is a sum of some monomials that appear in f. It might be all, it might be just one. And then I can extend this to ideals. So if I have an ideal in a polynomial ring, I can define its initial ideal with respect to w as the ideal that is generated by all the initial forms. So, for example, if this was my polynomial in two variables, x1 and x2, with x1, x2 squared plus x1 squared plus x2, and as weight I choose 1, 0, so x1 gets weight 1 and x2 gets weight 0, then I can compute the weights of all the monomials that appear here with non-zero coefficient, and I realize that x2 is the only one that has weight 1. The others have weight 2, so the initial form will just be x2. And I'm sorry if this is very boring and basic for you, but I wanted to make sure everyone just, you know, gets what I'm talking about. Okay. So from this very kind of simple setup, I can go on and define the Gröbner-Fan and Gröbner degenerations for you. So if I now have an idea in a polynomial ring, its Gröbner-Fan is going to be all of r to the n with a fan structure. And that is exactly defined by taking the initial form. So I say two elements, v and w, they lie in the relative interior of one cone. And I denote the relative interior with this little circle here. So this is the open cone, C. And I say they lie in the same cone if and only if the initial forms or the initial ideals of my ideal J are equal with respect to v and w. So that means in particular, I can adopt the following notation. I can talk about the initial ideal with respect to a cone. And what I mean by that is just pick some element in the relative interior of that cone and compute the initial ideal with respect to that. And by definition of the fan structure, this is always going to be the same ideal. And the Gröbner fan is very interesting for the following reason. It gives me lots of degenerations of my variety. So if I choose any open cone now, this is in correspondence with one of these initial ideals, and it actually defines, or I can define a flat family that is going to be a morphism from some variety v to a1, such that a flat morphism such that the fiber over any t in a1 that is not 0 is going to be isomorphic to the vanishing set of my ideal, and the vanishing set over the origin is going to be isomorphic or equal to the vanishing set of my initial ideal. So in that sense, if I have some variety that is embedded into an affine space or projective space, I can define lots of degenerations of this variety just by looking at different points in R to the n, where n is the number of variables. But most of these degenerations are not too interesting, maybe because if I pick just a generic point in R to the n, the initial ideal would just consist of monomials, so it would be generated by monomials. So geometrically, this might not be the object we're interested in. But let's look at an example first, how this Gröbner fan looks like. We're going to take now the ideal that is generated by the polynomial that we saw on the slides before. So it's again in two variables. My ideal is just generated by one element. The Gröbner fan now is R2 because I have two variables, and the fan structure looks as follows. So I have three maximal cones that are here color-coded. I have three one-dimensional cones that are their intersections or the rays of this fan. The initial ideals with respect to the maximal cones are generated by monomials. I have three monomials in my polynomial, and these are exactly the three possible monomial initial ideals that I will get. And at the intersections of two maximal cones corresponding to monomial initial ideals, I get binomial initial ideals that consist exactly of the binomial that has the two monomials of each maximal cone. So this is what the Gröbner fan looks like for this ideal. Okay, and this observation is in fact true in general, like the observation that the maximal cones correspond to monomial ideals. And this in fact leads us to standard monomial bases. So the first type of basis that will appear, as I mentioned before, I'm interested in toric degenerations that share a basis, whatever that means so far. So we're getting close to the first instance of that. I will now denote the quotient of my polynomial ring by my ideal by A. And for every tau, every cone in the Gröbner fan, I denote by A tau the quotient of the polynomial ring by the initial ideal. If I now fix a maximal cone in the Gröbner fan, as I mentioned already, the initial ideal with respect to that cone is going to be generated by monomials. So in particular, for every face of such a cone, I will define the following set. BCT that consists of cosets of monomials in the algebra A tau. So A tau is my quotient. X alpha would be a monomial in the polynomial ring itself. And then this little bar here should denote that I'm in the quotient. And I take all these cosets of monomials that don't lie in my initial monomial ideal. So it's quite easy to see maybe that this set, in case I take here AC, the quotient by the monomial ideal, then this set is a basis for that algebra. But in fact, it extends, and this set BC tau for any tau that is a face of C is a basis for the quotient A tau. And this is called standard monomial basis. So these bases, they arise in standard monomial theory that was introduced by Lakshmibai and Seshadri, and then generalized by Stromfels and White and many others. So in particular now, if I choose the cone, the apex of the cone, the origin, to be the face I look at, then this set BC0, I can also denote it by BC, and it's going to be a vector space basis for my algebra A, so the one I started with. And the observation now here is, so every tau, every face of the cone defines me a degeneration, as we've seen on the slide before, and all these degenerations now share one standard monomial basis. So all the coordinate rings of the affine cones of the varieties that arise here have one basis that is indexed by exactly the same set. And this is in fact very powerful, as we will see in what comes. Okay, so if there's no questions, I will just keep moving on, but feel free to interrupt me. Now I can define for you the construction, or the main construction of our project. So we will now choose one of those maximal cones in the Gröbner fan. And from this point on, I will think of a J as being a homogeneous or a weighted homogeneous ideal. So defining a projective or a weighted projective polarized variety. And for this cone, I will now choose its ray generator. So that can just be the primitive ray generators of the cone. And I will label them R1 to Rm. And define a matrix R whose rows are exactly these ray generators. Now I take any element in J and I can define its lift. So what is that? I take F, and now F, usually I can think of it as a function in x1 to xn, but instead of evaluating just in x1 to xn, I will plug in monomials and T's. So T's, I have one Ti for every ray, and the multi-exponent of this monomial that I put in front of x1 is exactly take this matrix R of rays and multiply it with E1. So R is a matrix of size m times n. N is the number of my variables, and E1 is going to be the standard basis in z to the n. So if you want the exponent vector of the monomial x1. And I do that for all xi's, and then in the end here, I multiply by a monomial in T's that has as exponent for every ti the minimum of all the dot products between ri and alpha. So these dot products, we've seen them before when we take initial form. So this is like taking the initial form with respect to a ray, if you like. Yeah. So we run over all the monomials in F, and we take these dot products of rays with exponent vectors that appear with non-zero coefficient. And then similarly, we define the lifted ideal, and that is going to be generated by the lifts of certain elements that are in my ideal. And I will choose as a generating set for my ideal, I will choose a reduced Gröbner basis for J. So that means in particular, a reduced Gröbner basis is a generating set for the ideal, such that the initial forms of these elements, now the initial forms with respect to this maximal cone C, such that they also generate the monomial ideal. And then reduced just means that I take a certain minimal such generating set that that is reduced in the sense that I cannot express elements in terms of combinations or of others in the same set. Okay, so this is the definition of my lifted ideal. And this is going to be the base of the family I'm going to define. So, but before we go any further, let's look at the example again that we saw in the start. So we take the same polynomial in two variables, x1 and x2, and we focus on one maximal cone and its Gröbner fan here that has associated initial ideal, the one that is generated by the monomial x2 only. Now, this cone is spanned by two rays, R1 and R2, and the primitive generators here are 1, 2, and 1 minus 1. So now I will just use my definition of the lift and compute the lift. So I plug in here these monomials. So what is this again? My matrix R has now first row 1, 2, and second row 1 minus 1. And the exponent of this monomial is take this matrix and multiply it with the exponent vector 1, 0 of x. So I get exactly the first column of the matrix R. So that's 1, 1, 1 for T1 and 1 for T2. And then the same for x2, I get the second column. So this is 2 minus 1. And back here, I have these, the monomial in T's, whose exponents are minus the minimum of the dot products of array with all the monomials. So for example, for T1, this minus 2, where does it come from? For T1, I look at the array R1 and I take the dot product of R1 with all the exponent vectors in my monomial. So here I get the dot product of 1, 2 with 1, 2. I get the dot product of 1, 2 with 2 and of 1, 2 with 0, 1. And the last one is the only one that has dot product 2. And this is in fact the minimum. So my exponent for T1 is minus 2. Okay, so the same goes for T2. And now I can actually plug this in and compute, and I see the outcome is actually a polynomial in T's and in X's. Or if you like, it's a polynomial in X's that has coefficients, monomials or polynomials in T's. And I've written down this F tilde here as being dependent on T1 and T2. That's exactly because I want T1 and T2, I want to think of them already as the deformation parameters of my family. So now I can plug in different values for T1 and T2 and see what happens. Well, first of all, if I plug in 0 for both of them, I'm left with x2, which was exactly the initial form of my polynomial f with respect to the maximal cone I've chosen. And well, then I can plug in 1 for T1 and 0 for T2. And I compute the outcome, and I see this is exactly the initial form with respect to the array R1. And then I can do the same for 0, 1, and it's going to be the initial form with respect to the ray R2. And then lastly, if I plug in 1, 1 for the t's, or more generally some generic t's, then I can obtain back my polynomial t, or with different complex coefficients. Okay, so this is essentially this observation goes through, and this is going to be our first theorem today. So let's now consider the quotient, the algebra that is the quotient by a polynomial ring that not only has the variables x1 to xn, but also the variables t1 to tm. And this jc of t here, that was my notation for the lifted ideal. Right, so C is my maximal cone. I've chosen the rays, I've lifted all the elements, I've lifted the ideal, and I look at these quotient algebra now. And then the first result is this algebra AC is a flat CT1 to TM module. So in particular, I can take spec of it over AM, and this is going to be a flat family. So I get a flat morphism from the spectrum of my algebra to the affine space AM, and the AM here has exactly coordinates or variables T1 to Tm. The generic fiber of this family is going to be the vanishing set of the ideal I started with, and then I get a bunch of special fibers. So for me, special fibers is every fiber over a point where at least one of the t's is equal to 0. And then those special fibers will be isomorphic to the vanishing set of various initial ideals of J that correspond to faces of C. So in particular, if I go to the origin in my affine space, I will find as a fiber something that's isomorphic to the vanishing set of the monomial ideal associated with the cone. And then as I move around and some t's are non-zero, I get the corresponding vanishing sets of initial ideals that are associated with the faces of tau. So this is essentially the observation we made on the slide before, but a bit more general. So yeah, so if we get back to the example, this algebra AC will now be the quotient of the polynomial ring with 4 variables, T1, T2, X1, and X2. And this right here, the ideal that is generated by the lift of F, because in this case, our ideal was just generated by one element, and the reduced Gröbner basis that I mentioned in this case is also just this element, and hence the lifted ideal, by my definition, is just the ideal generated by the lift of that element. Okay. Okay, so so far we did not really see toric degenerations. I told you about some kinds of Gröbner degenerations, or all kinds of Gröbner degenerations, but they can be in general quite wild, and maybe geometrically they don't really have properties we want. So let's get back to the motivation, and let's look how toric degenerations arise in this setting, or where we can find them. So the Gröbner fan, that was R to the n for my ideal J, contains a particular subfan that's of the yeah. Okay, so the Gröbner fan contains a subfan that is of dimension, the Kroll dimension of A, or equivalently the dimension of the affine variety that is the vanishing set of my ideal. And the subfan is called the tropicalization of J. And it is defined as follows. So if I R to the n, my Gröbner fan has support R to the n, and now I focus only on those elements whose initial ideal does not contain any monomials. So for example, I get rid of the maximal cones. I told you the maximal cones are generated by monomials, so I get rid of all of those. But then in between cones whose initial ideal does not contain any monomial and contains only monomials, say it was generated by monomials, I've got a bunch in between. So the dimension of the maximum cone in the Gröbner fan is the dimension of the ambient space where my affine variety lives. And here I have a fan that is of dimension of my variety. So everything in between the dimension of the affine space and the dimension of my variety will contain monomials. And then, but this can be even more exclusive. So a straightforward corollary of the result we've seen on the other slide is now, if I consider the fan that is the intersection of my maximal cone C with the tropicalization. So note here, C is, it lives in the Gröbner fan, is a cone there. The tropicalization is a subfan of the Gröbner fan. So if I intersect those two, again, I naturally have a fan because everything takes place in one fan. So the fan structure here is still the one from the Gröbner fan, but I got rid of all the faces of C and its relative interior that whose initial ideals contain monomials. So now if I have in this fan sigma some tau, so that the initial ideal with respect to tau is a binomial and prime ideal. So binomial means just generated by binomials. In particular, it satisfies this condition, and it's also the furthest I can go. If I have a binomial ideal and I further take some initial ideal of it, most likely I will create some monomial. So this is this corresponds to a maximal cone in this tropicalization. And if the ideal is binomial and prime, this means the vanishing set is a toric variety. So my family pi C that I've seen on the slide before contains toric fibers isomorphic to the vanishing set of this initial ideal. Right, so this is how in this setting I may find toric degenerations, and I may find them only because I don't know if such cones exist, and most likely in general they don't. It's a bit of a challenge given an ideal to say if such cones exist in the tropicalization or not. But if they do exist, I'm lucky, and I find these toric degenerations. And in nice cases, I will find toric degenerations. And nice cases would be, for example, Grossmannians or flag varieties, or any kind of variety that has lots of symmetry is most likely going to have such a toric degeneration. Okay, so let's quickly look at the example again of what this the tropicalization is, what the subfan is for my ideal J from before, being generated by this one polynomial into variables. My tropicalization has three one-dimensional cones, so my variety is one-dimensional, the affine variety in A2 here is one-dimensional, so the tropicalization is one-dimensional, and these three cones are the rays that we've seen before. So given the Gröbner fan, we had like, the support of the Gröbner fan was all the space here, but now given this condition that we want only points whose initial ideal with respect to J, or the initial ideal of J with respect to that point, does not contain a monomial, we get rid of these monomial cones, and we're left with arrays that had binomial ideals associated to them. So now if we go back to the example of the family, I chose a few slides ago the cone C here, generated by the rays R1 and R2. So the intersection of C with the tropicalization is exactly the union of these two cones that are just rays. And in fact, the vanishing set of the ideal associated to R1 is a binomial prime ideal, so it's a toric variety. So I excluded the vanishing set of this ideal, the one associated to R2, because the ideal R2 is not prime, right? But if you extend your definition of a toric variety, you may want to include it as well. Okay. So That was everything on the general construction or the general picture so far. And if there's no questions, maybe you can check this. I think I cannot see the chat, but later eventually.
There was
Okay.
a question, but it's already answered, so you can have a look later.
Okay. Okay. Sorry. I think I'm not sure if I don't know how to see the. Oh no, now I see the chat.
You might have the chat function on the bottom, and if you click on that, it should come up.
Yeah. So so it was answered in T.
So the question was basically if when you have this definition of the lift polynomials, you had some negative powers of t, right? And you are sure always that the result will be still a polynomial, so it would not be rational, right?
Yes. So let me quickly go back to that slide. Maybe actually that was a confusion I also had a while ago, but in the definition here, if you look at it, so what happens if I plug in here this for x1, this monomial in t times x1, then my the exponents of my t's here will be this dot product. So when I have a monomial somewhere, x alpha, then by plugging in these t's as well, I will have a monomial that in t's whose exponent vector is the dot product. So every ti has exponent dot product of ri with alpha. And all I subtract here is the minimum of these dot products. So at most, I will get rid of of this of the minimum. I will get to 0. That is assuming that my matrix has non-negative entries, but I can make that assumption.
Right. Yeah. Of course.
Yeah, exactly. Yeah, and I can make that assumption if my ideal is homogeneous or weighted homogeneous. So this is essentially why I make this. Well, I restrict to projective or weighted projective varieties, although I'm generally interested in projective varieties. So for me, that's not really a restriction. Okay, that was all in the chat, or?
Yeah.
Okay, perfect. Thank you. I'm sorry. I've not seen it before. Okay, so then we were here. Yeah, so we're ready for the first application, and it is to universal coefficients for cluster algebras. So I don't assume you know what a cluster algebra is. If you don't, just relax for like 2 minutes and then you can come back. If you don't, I will give you more like an intuition of what it is rather than the precise definition, because it gets a bit technical. So a cluster algebra is important for us. It's a commutative ring and it's embedded in some ambient field. So it's the domain. It is defined recursively by seeds, and seeds are maximal sets of algebraically independent algebra generators. And I will call elements of a seed cluster variable. So I've got lots of these seeds. In general, I have for an algebra, I have lots of different sets that are algebraically independent algebra generators. But here I have an extra condition that is combinatorially. So I don't choose arbitrary sets of algebra generators, but I choose one, and then I apply a procedure or an operation that is called mutation. It takes one of those seeds, replaces one element inside it by another to give me a new seed. Right. So this procedure gives me a bunch of seeds of sets of algebra generators, and they are connected in a certain way that is combinatorially. And this process of getting a new seed is called mutation. Now, if I consider the Grossmanian, maybe my favorite variety with its Plucker embedding, I can look at its homogeneous coordinate ring. So it's generated by the Plucker coordinates Pj that are indexed by subsets with k elements of 1 to the n, in the case of the Grossmanian kn, and I quotient by a homogeneous prime ideal, that is the Plucker ideal, and that I will denote it by ikn. And then Scott showed in 2006 that this algebra, this homogeneous coordinate ring, is in fact the cluster algebra. Now, if my k is less or equal than 2, the Pluker coordinates are in fact all coordinates I have, all cluster variables I have, I'm sorry. But if my k is greater than 3, and I have this small assumption here that k is less or equal than the lower bound of n-half, then Pluker coordinates are still cluster variables, but I have more cluster variables than Pluker coordinates. Now, if there are a few cases where I end up with finitely many seeds, and those are exactly when k is 2, or k is 3, and n is 6, 7, or 8. And any other Grassmannian will have infinitely many seeds and infinitely many cluster variables. So this already shows you maybe a bit that, that cluster algebras are maybe a bit tricky to deal with, because we start with this algebra that has a very nice presentation by finitely many variables that form sets of algebra generators. But if we look at it as a cluster algebra, we get generically, or if the Grassmannian is big enough, infinitely many seeds and infinite many sets of algebra generators. Okay, so now we can use the cluster structure on the Grassmannian, or more generally, whenever an algebra is a coordinate ring of some variety and has a cluster structure, or is a cluster algebra, we can use this cluster structure to define toric degenerations of the variety. And that is roughly as follows. Again, this is the idea of how it goes rather than all the technical details. So now if I fix one of these seeds, one of these sets of algebra generators, and I can endow my algebra with principal coefficients at that seed. And what that means, or what that does, better is it gives me an algebra A prin S. That is a subalgebra of still rational functions in x1 to xn, but now I have coefficients in polynomials t1 to tn. But this story is very nice. So if I put some technical assumptions on my algebra here, then this algebra A prin S has a ct1 to tn basis that is called the theta basis. And the nice thing here really is also that this theta basis is independent of the seed S. So if I choose a seed, then this algebra with principal coefficients does depend on my seed, but it has a basis that does not. So whatever seed I choose here, all these principal coefficient algebras have the same basis, or as we've seen and for the standard monomial basis, they are like indexed. These bases are always indexed by the same set. And now if A, so the cluster algebra I started with, was the homogeneous coordinate ring of a projective variety, then this algebra A prin S defines a toric degeneration of x to some toric variety x S0. So my algebra has a ct1 to ct basis. In particular, it is a free module, so I can, in particular, flat. And I get this flat family by taking spec of this algebra over the affine space with variables t1 to tn. And all these degenerations share the theta basis. So this is like the second incidence or example of a bunch of toric degenerations of a projective variety that share a common basis. And yeah, and here we have, again, the same phenomenon. We have lots of toric degenerations and all algebras defining the families and defining the toric varieties have a basis that is indexed by the same set. Now we can go one step further from this construction, and we can try to already patch these degenerations all together. So here we have all these algebras that one such algebra defines a toric degeneration, but as I mentioned in the start, I'm interested in combining these now and studying them all at the same time. And already that has a construction in cluster algebra, a corresponding construction, and it's called universal coefficients. So for now, I will assume that the cluster algebra has only finitely many seeds. This is a technical assumption. There is There's ways to deal with universal coefficients beyond finite type, but for the application that I will mention in a few slides, this is all I need. So let's, for simplicity, make this assumption that we only have finitely many seeds. In particular, we only have finitely many of these principal coefficient algebras to paste together. So we can take again now the cluster algebra A and endow it with universal coefficients. That will give us an algebra that is, again, rational functions in x1 to xn, or a subset of that field, but the coefficients changed now to polynomials in the variables t1 to t, the number of cluster variables. So I made this assumption that I have finitely many seeds. As a consequence, I have finitely many cluster variables, and this is just a finite polynomial ring. And the coefficients are called universal coefficients because of some universal property they have. And the important part of this universal property for us right now is that there exists some specialization map. So for every seed S, I will get a map of algebras of the universal cluster algebra, the cluster algebra with universal coefficients, to the one with principal coefficients. And I get that for every seed. And well, this map preserves all the nice properties that we would want it to preserve. So. Okay, so the upshot of this universal coefficients is that somewhat this algebra A unif knows all the toric degenerations of my projective variety. But the downside is that as it is a cluster algebra, it is defined only recursively. And in fact, if you start with a reasonable big enough cluster algebra, to actually compute this universal cluster algebra, even in finite type, gets a bit messy. Because even if we have finitely many seeds, there might be, I don't know, 800 of them or whatsoever. And then doing this computation is kind of nerve-wracking, I would say. Okay, but now comes the application. And the good side, like the good news I can bring to you if you're interested in universal coefficients for cluster algebras. So we consider the Grossmannian Kn, and as I made this assumption that my cluster algebra has finitely many seeds, I will focus on these cases. So my Grossmannian can be a Grossmannian 2n or the Grossmannian 3/6. Then we can write down another presentation of the algebra AKN. So that was the homogeneous coordinate ring of the Grossmannian with respect to the Plucker embedding. And I can present it now as a quotient of a polynomial ring in all cluster variables by some ideal JKN. And this ideal JKN is actually not too far from things we know and we're familiar with. So if I chose the Grossmannian 2n, if you remember a few slides ago, I told you that these cluster variables that appear in the cluster structure, they are the same as Plucker coordinates. And hence, the ideal JKN is the same as the ideal I2n, that is just the Plucker ideal that we already know. However, if I'm in the case of Grossmannian 36, then the set of cluster variables contains all the Plucker coordinates, but I have two more cluster variables that are x and y, maybe, if you want to call them like that. And then the ideal I36 is an elimination ideal from the ideal J36. So if I take J36 and I eliminate the variables x and y, I will get back the Plucker ideal. And this ideal JKN, in fact, and in both cases, is homogeneous for the Grossmannian 2n or weighted homogeneous for the Grossmannian 3/6. So I'm perfectly fine in the setting of the construction I told you about. And I can now apply our result. So the theorem goes as follows. I look at the Gröbner fan of this ideal JKN of the presentation of my cluster algebra, and I identify in there a unique maximum cone C such that there's a canonical isomorphism between this quotient AC, the family I defined, and the universal cluster algebra. So the right-hand side is here, take the cluster algebra AKN and endow it with universal coefficients. If you are familiar with cluster algebras, this means I start with a cluster algebra with frozen directions, and on top of that, I put coefficients that are universal coefficients. And because I'm always working with the tropical semifield, this will in the end be a cluster algebra that has the frozen vertices or the frozen variables I had before, and additional frozen variables for all mutable variables that are the ones that I get by putting these universal coefficients on top. But this is just a slight generalization of universal coefficients as they were introduced originally for cluster algebras without frozen directions. Now, the second point is that the standard monomial basis of the algebra AKN, the homogeneous coordinate ring of the Grassmannian I started with, the standard monomial basis here coincides with the theta basis. And as I'm in finite type, the theta basis, in fact, is the basis of cluster monomials. And then additionally, if I look at the intersection of my cone C with the tropicalization of the ideal, then every maximum cone in this intersection that gives me a toric variety. So all these cones, or all these faces of C that are maximum cones in the tropicalization have associated ideas that are binomial and prime. And this is something that is quite rare, that you find so many, say, binomial prime ideals associated to these cones in this intersection. Okay, so that was, I think, yes, everything about the first application. So the upshot here is we found a way to write down a presentation of the universal cluster algebras in these cases. So you don't have to do this recursive procedure anymore. You just find the right presentation of the algebra, find this maximum cone, and then you get the universal cluster algebra in terms of generators and relations. Okay, so let's, in the last 10 minutes, talk quickly about the second application I mentioned. Although, again, I have to say this is more of a connection to other people's work than an application itself. So for this part of the talk, we take the ideal I, an ideal I that is a homogeneous prime ideal, and we tropicalize it, and we hope that there exists some maximum cones in the tropicalization with the following properties. So we assume these things, actually. We have these maximum cones sigma 1 to sigma s in the tropicalization such that all their initial ideals are toric, the binomial prime ideals, and all of them are faces of one maximum cone in the Gröbner family. And then we denote by sigma the fan that has maximal cones sigma 1 to sigma s. So it's a subfan of the Gröbner fan, and its support are exactly these cones. Then there's a theorem by Kumars-Cave and Chris Mannon that tell us in this situation there exists a toric family that is a map, a flat family, a flat morphism from spec of R sigma, and I will tell you in a second what that is. And the base of this family is the toric variety associated to my fab. Right? So any fab, I can associate a toric variety or toric scheme with it. This is this TV of sigma. The generic fiber of this family is the vanishing set of my ideal. And then over every torus fixed point in the base, I get a special fiber that is isomorphic to the vanishing set of my initial ideal. And as I made the assumption that the initial ideal is toric, all these varieties are toric. So I get some nice family over a toric base with lots of toric degenerations combined in them. Now this R sigma, this curly R sigma, is a flat sheaf of Riesz algebras over my toric variety. And this bold spec is the scheme glued from the sections, from spec of the sections of this sheaf. So if I have an open subset in my toric variety, I I can look at the section or sigma of U of my sheaf, and I can take spec of that because that's an algebra. Okay, so that's to say this family in its construction is very different than what we've seen in the slides before. But however, we can, in exactly the setting, we can apply our construction because we have, well, we have a homogeneous ideal. If it's prime or not is not too important to us, but prime is of course always nice. And then we have a bunch of faces of this one cone that have nice toric varieties associated to them. So if we take this input now, the ideal I, and the cone C, we can apply the construction from before, and we get this flat family from spec of the quotient by the lifted ideal to the affine space. And the corollary is as follows. So if we look at sigma, let sigma be the cone as above. So the one that is whose support are these cones sigma 1 to sigma s in the tropicalization of J. Then for every point in the toric variety, that is the base of Calvi-Manor's family, there's a point in the affine space that is our base, such that the fibers are isomorphic, and they're isomorphic to the vanishing set of some initial idea with respect to some cone tau that is in fact the face of our cone C. And moreover, if the cone C is simplicial, we have a natural inclusion of the toric variety into the affine space. So if C is simplicial, then the affine space AM is nothing but the toric variety associated to C. And the cone sigma includes into C, so the toric variety associated to sigma includes to the toric variety associated to C. And we can draw the following diagram. So on the one hand side, we have this family, this toric family psi sigma. On the other side, we have our flat family pi C. Now the toric variety includes into the affine space, so the base includes into the other base, and we have that fibers over corresponding points. So if I take a point in the toric variety here and I look at its image in the affine space, then the fibers of these two families over the corresponding points are isomorphic. So what's the summary of this? So we have two flat families we can associate to this setting. One is the one with toric base, the other one is where the base is an affine space. Both degenerate the variety that is the vanishing set of our ideal to the toric varieties that are associated to these toric ideals we found in the Gröbner fan, and they all share a common basis. And in this case, the basis is again the standard monomial basis associated with the maxima cone C. Now, psi sigma has nice geometric properties. It's T equivariant and has reduced and irreducible fibers, for example. But the construction is not very explicit. We have to get this Ries algebra, this sheaf of Ries algebras, and take a spec of this sheaf of algebras. Pi C, on the other hand, has not such nice properties. For example, we have lots of non-irreducible fibers. The generic fiber is the vanishing set of a monomial ideal, so we're far from being irreducible in general. But the construction is quite simple in the sense that we just need to compute a finite generating set for the ideal, and the algebra is the quotient, and it's well adapted for computations. That is, if you already know a Gröbner basis for your ideal with respect to the cone, the rest of the computation is simple. And that's it. Thank you very much for your attention. And I will leave you with some references.
Thank you very much, Lara, for the very nice talk. It was very inspiring. Maybe we can unmute ourselves and just clap, or you can put it up in the reactions. Are there any questions? So there's nothing in the chat here, but maybe somebody wants to ask a question, then please go ahead. Maybe let us know. Just unmute yourself and ask the question.
I have a question. Actually, I have two questions. So in this construction for the Grossmannian, I mean, maybe you said it and I didn't catch it, but how do you sort of identify this unique maximal cone in the Grübner-Fan? Or can you identify it? I mean, or do you just know it exists?
No, we can identify it, and we have an explicit description in terms of its rays. In fact, for our construction, it is necessary to have very explicit knowledge of this cone. For the Grassmannian 2n, you can kind of make an educated guess based on the combinatorics, because everything is encoded very nicely in these triangulations of n-gons or disks with n-marked points. So there you have a nice guess of what it is. And for the Grassmannian 3/6, so if we go back maybe quickly to this ideal JKN, that is the presentation of the homogeneous coordinate ring of the Grassmannian. This idea contains, for example, all the exchange relations of the cluster algebra. And in fact, the monomial idea we want contains all the non-cluster monomials in the exchange relation. So the exchange relation, if you remember, is on the left-hand side. I have a product of cluster variables that are exchangeable, and the right-hand side consists of cluster monomials. And these non-cluster monomials, these exchangeable exchange monomials, say, they should all be contained in my maximal cone, so that in the end there's a chance for the standard monomial basis to match with the cluster monomials. And then it's about finding a nice weight that gives you a monomial idea that contains all these exchangeable monomials. In fact, it was quite useful to look at this categorification picture, these diagrams. You can draw that, encode the cluster category to make a guess, like what should be the weight you put on which variables.
And okay, so then if it's so explicit, so why? What is the problem with 3.7 and 3.8?
Yeah, the problem is the size, I would say. So technically, yeah, it's completely possible to do the same. But the first thing we had to do was compute explicitly all the exchange relations, for example. So for Grassmannian 3.6, this is 52, I think. But then for 3.7 and 3.8, they're of type E6 and E8, I think. So E6 already has like 800 something seeds. Or E8, I don't know. Like it gets big.
So you really need the explicit calculations.
In this case, yes. But by now we have some better, a bit more conceptual understanding, and we hope that maybe in a follow-up we can see if we can do something similar for finite type cluster algebras, if we know enough.
Okay, thank you.
Are there any more questions?
My question overlaps a little bit with Sibylla's, but just to clarify, the theorem on the next slide still has this assumption on Kn, so is that right?
Yes.
Yes, it's for these.
Yeah.
And you said that JKN includes the exchange relations, but it has more, or it's just generated by the...
Yeah,
okay.
this was very interesting. So for I2N, the Plucker relations are all exchange relations.
Sure.
So there's nothing happening. But then surprisingly, for the Grassmannian 3.6, the idea generated by all exchange relations is not prime. We were also a bit surprised by that. But there's already, so to define the Grassmannian, you already need more than, or some varieties isomorphic to the Grassmannian, you already need more relations. And in fact, what's missing here is one 4-term Plucker relation. And then additionally, to lift everything, the reduced Grübner basis has one more element as well. So in the end, the important relations for us are all exchange relations and 2 4-term relations, or higher 4-term relations. So yeah.
Which you don't have a cluster explanation for. You just appear them somewhere.
We were thinking about that. Yeah, no, there is a cluster explanation. So in fact, in the end, these monomials in the monomial idea, this monomial idea will be generated by monomials that are of degree 2 and that are pairs of cluster variables whose compatibility degree is positive. And then for the Grassmannian 3.6, all exchangeable cluster variables have a positive compatibility degree, but there's 2 more pairs of cluster variables that are not exchangeable, at least not directly, like 2-step exchangeable if you like, but their compatibility degree is positive. So already in the cluster structure, you see that you need more relations than exchange relations.
Okay, very good. Thanks.
Any more questions?
Hi, yeah, I had a question. I just wondered if there was a role for the frozen variables in the Grossmanian cluster algebra in your picture, or do you just look at the cluster variables basically?
No, we look at all. So we look at all variables. So from the Gröbner perspective, there's no difference between frozen Plücker coordinates and Plücker coordinates.
Sure. So when you add the kind of coefficients to the algebra, those are in addition to the frozen variables.
Exactly.
Okay, cool. So you kind of distinguish between frozen variables and coefficients somehow.
We kind of distinguish. Yeah. So in the family, in the end, this family over the affine space, the coefficients are the variables of the base, and the frozen variables are just variables of our variety, coordinates of our variety. So there's the distinction. Yes.
Thanks.
Thank you.
I had one question. When you compare the 2 tropical families, I don't know which slide it was, a bit later. This theorem. One more, I think. Yeah.
Here. Yes.
Exactly. So in which way can you say that your family you constructed there is kind of universal in a way that you can get other situations or families out of this? Does it have any universality property in some sense?
Yes. So universal. I would only use this word now in the context of with the universal coefficients for the cluster algebra.
Right.
Some universal property. Otherwise, I'm not sure. Like, I don't know of any universal property this family would have, rather than kind of, if you have a maximal cone, it includes all the possible degenerations that are associated with this maximal cone.
Right.
Well, there's something to be explored. What are other good properties this family has? In general, actually, I mean, even if you start with the prime ideal, it's not clear that this quotient algebra AC is a domain. It might not be. Like in our applications now with the Grassmannian, it turned out to be a domain, but we only know that because we could identify with the universal cluster algebra, which we know is a domain. So it's a bit tricky so far in general to say what can happen, because the construction itself can just be applied to arbitrary ideals, essentially.
Okay, thank you.
Thank you.
Are there any more questions or comments? If it's not the case, then let's thank Lara again for the very nice talk.
Thank you.
We will have a seminar next week by Wendy Lowen from Antwerp, and it will be again at 1 o'clock at the normal time. So hope to see you all next week, and have a nice weekend. Thanks again, Lara.
Thank you.
Thank you.
Bye-bye.
Bye.